Hi, welcome to you all for this videos. So today we will discuss about the fins. So first we should know the definition of fins. So it is a device used to enhance the convective heat transfer rate by extending the surface area through which heat is transferring. So what is the definition says that? So fin is one device. So that device is used to enhance is nothing but increasing the convection heat transfer rate. So that how to increase that? Extending the surface area through which heat is transferring. So this is by extending the surface area so that extending surface area is called as fin. Whatever the extending surface area is there, so that is called as a fin. So that fin is used to enhance or increase the rate of heat transfer through convection mode of heat transfer. So we know that for convective heat transfer we have that Q is equal to HA delta T. So here Q is nothing but rate of heat transfer, H is convective heat transfer coefficient, A is surface area, and delta T is the temperature differences. So in order to increase the Q value, that is rate of heat transfer, so out of these three one must be increases, that is H, A or delta T. So this we know that this is constant and this delta T is also constant, take it as a constant. So only possible way to increase the rate of heat transfer through convection is by increasing the surface area. That's what here in the definition it says, that extending surface area. Let's just take a small example here. Here we are having one surfaces, or you can say it is a base of the material, so that is maintained at 100 degrees Celsius, and the surrounding temperature of that material is maintained at 20 degrees Celsius. So that delta T is nothing but 100 minus 20 degrees. All of you know that about. So now how to increase this surface area? Now if you take this one, so here the surface area is this much, only this much. So if you observe this second figure, so what happens here some extending area is there, that is the surface area of that fin, surface area, or you can say it is a fin or increased or extending surface area. So by doing this we can increase the surface area as well as we can increase the rate of heat transfer through the convections. So this is about the definition of fins. So now let's move on to the types of fins. So there are mainly 5 types of fins are there. 5 types. So in that first one is uniform cross-sectional rectangular fin. So that nothing but, so this is the base plate, and here it is extending surfaces or fin. So this extending surfaces or fin, its shape of this fin is uniform cross-sectional and rectangular type. Uniform cross-sectional means its area throughout the length of the fin is uniform. So this is a first type of fin. So next one is second type. Here, so in this is the second type, is tapered fin. So as name indicates that the extended surface, whatever the extended surface from the base plate is, it is in the form of a tapered shape. So that's why it is called as a tapered fin. Now third one is a splint type fin. So usually this type of fin is used where the surface area or the base material is in the form of cylindrical. cylindrical. On that cylinder we are having some slots, so that slots is called as a spline type pin or extended surfaces. So next, fourth one is disc or annular type. So this type of pin is nothing but, here there is one rod or circular pipe, so surrounding that pipe we are having that extended surfaces. It is in the form of, or its shape is in the form of disc, so that's why it is called as a disc or annular type. So next, fifth one is fin. Fifth type of fin is fin. So on a single base material we are having different types of fins. We are attaching the different types of circular, cross-sectional, rectangular and taper. So that type of pin is called as fin. So this is fifth type. So these are the five types of pin. Now uses of pin. So here you can use these pins. So first we are using this pin used in a radiator of automobiles. Automobile radiators we are used for the cooling purposes or in order to increase the heat transfer rate. And second one is air cooled design cylinder head. So I think all of you observe in your bike. So in that bike we are observing this type of pins here. So this is a engine cylinder. So head of the cylinder. On that head of the cylinder we are having that spline type of fins. Okay. So next, fourth one is a transformer. So in the electricity, in the electrical field we are having the transformer. On that transformer again we are using the fins. And the fifth application or uses are condenser coil or air conditioning. So we are using the domestic air conditioning, that we are using these pins. Okay, so these are the uses of pins. Now this is about fin definitions, next types of fin and uses of fin. So next we will move on to the derivations. It is derive an expression for heat flow through the rectangular fin of uniform cross sectional. So we can derive one equation, that is temperature distribution equation and heat flow through the rectangular fin. So type of fin is here a rectangular fin. Before going to derive the equations, we have to make some assumptions. Those assumptions are steady state heat conduction along in x direction. Means there is no change in the heat conduction along with the x direction. It is steady state heat conductions. So next one is, second assumption is no heat generation within the element. There is no heat generation within that extended surfaces or fin. Next one is uniform heat transfer coefficient, that is H. So H is constant or it is uniform over the entire surfaces of the fin. So next, fourth assumption is a material is homogeneous or and isentropic. So whatever the extended surfaces or the fin material is there, that is made up of with a single material. It is a homogeneous material. Next, the last assumption is negligible radiations heat transfer. So in these assumptions indicate that there is two mode of heat transfer. One is conduction and another one is convection. There is no radiation heat transfer, so that we can negligible radiation heat transfer. So these are the 5 assumptions. Next, so to derive the equations that to derive the expression for the heat flow through the rectangular fin of uniform cross sections, we have to take some figures here. So here it is a base plate, this is a base plate, and this is the extending surfaces. Okay, so let us consider an element of fin of thickness dx, and at a distance x from the base plate or surfaces. The heat enters and leaves the element by conduction, so that this whatever the shaded area of the element is there, that you can take it in the separate way. So that is the element here, and that element is having the temperature of T. Okay, so what it states, the heat enters and leaves the element by conduction. So whatever the heat is entering into the element and leaving from the element is conduction mode of heat transfer. And and heat convected around the surfaces of the element. So there is no radiation heat transfer, but heat is convected around the surface of the element, So before going to derive, we have to see one energy balancing equations. So what is the energy balancing equations? So whatever the heat enter into the element, that is Qx, heat enter into the element is equal to heat leaving the element, that is Qx plus dx, plus heat convected from the element, So this is the energy balancing, or this is the energy balancing. Energy balancing is nothing but what? Heat enter into the element, so that the amount of heat enter into the element, which is equal to what? Heat leaving from the element and heat convected from the element. So heat is convected from the element. So this is a energy balancing. Next, before going to derive this, we have to see some equations here. So what I can do here, I can choose one linear differential equations, that is theta is equal to c1 e raised to mx plus c2 e raised to minus mx. So what I can do next is I can differentiate this theta with respect to x, that is d theta by dx. So c1 is a constant, keep it as it is, and m e raised to mx plus minus c2 m e raised to minus mx. So here again I can differentiate this one more time, that d square theta by dx square is equal to what? c1 m square e raised to mx plus c2 m square e raised to minus mx. So I can take this m square, it is common in both the term, I can take it outside, and we left with c1 e raised to mx plus c2 e raised to minus mx. So this is nothing but, this total term is nothing but our theta. So I can substitute this is with theta, so that d square theta by dx square is equal to m square theta. So I can take this in this side, it becomes d square t by dx square minus m square theta is equal to 0. Just we have to remember, so the solution for this equation, second order equation, is this one, linear differential equation. You have to remember this, d square theta by dx square minus m square theta is equal to 0. The solution for this equation is theta is equal to c1 e raised to mx plus c2 e raised to minus mx. So here you have to remember these two. Now we will continue with that derivations. So here it is heat enter into the element is equal to what? Heat leaving the element plus heat convected from the element. So first we have to find out this heat enter into the element. Here heat conducted into the element or enter into the element is given by, we know that conduction equations formula, that qx is equal to minus k dt by dx. So next, similar way, heat leaving the element is given by qx plus dx. So that qx plus dq, differentiation of this along the x thickness, and this is a distance. Okay, so it is taken as equation number 2 and it is equation number 1. Now the last one is, then heat leaving by the convection is given by q convection is equal to HA T minus T infinity. So equation number 1, 2 and 3. So we have that energy balancing equation is equal to heat entering into the element is equal to heat leaving from the element plus heat convected by the element. So we have to substitute all these three equations in that energy balance. So here it becomes, what happens, qx is equal to qx dqx by substitute, just we have to substitute all these equation in that energy balancing. So qx and this qx get cancelled. So what we left with, the dqx by dx into dx is plus HA T minus T infinity. So here d by dx, substitute this value, substitute the value of qx here, substitute the value of qx in these equations. So and keep it as it is, remaining term. So here we have to simplify it, take it outside, k d square t by dx square dx plus HA T minus T infinity is equal to 0. Now minus k d square t by dx square into dx plus h. So this surface area I can write it surface area as a perimeter into thickness, as next, same as it is, just keep it as it is, t minus t infinity equal to 0, because that surface area can be defined by perimeter into the thickness, both are same. Cross sectional area is different, but the surface area can be defined by perimeter into thickness. Now dividing throughout by Ka dx, we get d square t by dx square plus hp by K t minus t infinity equal to 0. So this is about simplifications. Next we will move on, we will continue the next. So next what happens here, d square t by dx plus m square theta is equal to 0, make it as equation number 4, where this m square is equal to hv by k and theta is equal to t minus t infinity. So here what I can do, this theta, I can differentiate this theta with respect to x, that then it becomes d theta by dx is equal to d theta by dx. Again differentiating, d square t by dx square is equal to d square t by dx square. Okay, from equation 4 and 5 you can write d square theta by dx square plus m square theta is equal to 0. So whatever this equation is gives us describe the temperature as a function of x. This equation is describe the temperature as a function of x. So in the previous one, here we know that d square theta by dx square minus m square theta is equal to 0 is equal to what? Theta is equal to c1 e raised to mx plus c2 e raised to minus mx. So what I can do, I can write directly the solution of this equation as theta is equal to c1 e raised to minus mx plus c2 e raised to mx. So here C1 and C2 are the arbitrary constant. So these constant can be obtained by applying the boundary conditions. So there are 4 types of boundary conditions are there. So we will discuss about those 4 type of boundary conditions in next video. Thank you. I hope you understood. If you have any doubt, ask me. Okay, thank you.